First of all, I would like to pay my respect to teacher. My name is Yu Sok Manat. I am a member of Group 3. In Group 3, there are consist of 3 members. First one is me, and the other 2 are Lam Heng and Lam Panat. Our group is going to present about Chapter 3, which is covering on transmission network planning and optimization. Before we are going straight to present about the chapter, let me define you some important keywords in the chapter first. The first one is what is the transmission network planning? After we have been research about the question, we have found out that the transmission network plannings involve assessing the current and future power demand for a region, as well as evaluating the reliability, capacity, and efficiency of the existing transmission infrastructure. Moreover, based on the assessment, new transmission lines, substations, and other facility may be built and existing facility may be upgraded or expanded to meet the future power delivery needs. Let's move to the second keyword. What is transmission network optimization? The transmission network optimization is the process to improve the performance of the transmission network through the use of advanced technology and operational systems. Thus, the transmission network planning and optimization is referred to the process of designing, building, and managing a power transmission network to ensure effective and efficient power delivery to all users. And here is the content of our chapter. As we know that the transmission network planning and optimization is not an easy topic to understand. So, in order to make it easier to understand and to learn, our group has divided into different sections to learn. The first one is about the basic of transmission network planning. Second is about the elements in a transmission network. Third, we will learn about the transmission pre-planning. 4. We will learn about the detailed transmission network planning. 5. We will jump to the transmission network optimization. 6. We will figure out about the GPOS transmission network planning and optimization. And the last one, we will learn about EDGE transmission network planning. So let's take a look to the first section about basic of transmission network planning. In this section, we have divided into 2 parts. The first part is about the scope of transmission network planning, and the second is about the elements of transmission network planning. Let's take a look to the scope of transmission network planning. In the GSM system, the scope of transmission network planning is generally considered to be the network between the base stations and the transcoder submultiplexer TSCM. So, what is GSM? GSM, or Global System for Mobile Communication, is a set of mobile communication standard and protocol governing second generation. We always call it 2G network. It first developed and deployed in Europe. Moreover, the GSM system managed communication between mobile station, base station, and switching system. As you can see in this picture, the GSM architecture is made up of 3 central systems. The first one is mobile station. The second one is NSS, or we can say network switching system. It provides flow management and call processing for a mobile device between base station, moving between base station. And the last one is BSS, base station subsystem. It is in the middle between the mobile system and network switching system. BSS serves as the connection between the network subsystem and the mobile station. Let's take a look to the circle here. The circle here shows about the scope of the transmission network, which is the network between the base station and TSCM. Based on its location and functionality, it acquires an important position in the mobile network infrastructure. As you can see here, because it connect the radio network to the mobile switching center, MSC. So let's take a look to the second part about the element in the transmission network planning. In the transmission network planning, there are three elements. The first one is about the BTS, base transceiver station. The second element is about BSC, base station controller. And the last one is about TCSM, transcoders and submultiplexer. So let's take a look to the first element of the transmission network planning. As I just mentioned above, BTS is or base transceiver station is one of the elements of the network planning system, transmission network planning. So what is BTS? BTS is a piece of equipment that facilitates wireless communicates between a device and a network. It's also a mobile phone network's infrastructure component responsible for carrying out tasks such as transmitting and receiving signal between cell phone and network. So, where is the BTS allocated? In the picture, you can see that the circle here is show about the base transceiver station. So, we can see that BTS is in the scope of base station subsystem, and on the other side, it connects to the BSC via the ABIS interface. Furthermore, the BTS also consists of a transmission unit, T or U. This unit interacts with the ABIS and other interface. T or U may be capable of making cross connection at the 2 megabyte per second level and drop and insert functionality at the 8 kilobyte per second level. Transmission units are capable of holding branching table, and this table guide the transmission unit on what to do with the traffic coming in from the PCM line. For example, should it just let it pass or for the next BTS, or should it drop some traffic mean from its own T or X? So let's move to the second element of the transmission network planning. The second element is the base station controller, BSC. So, what is BSC? Base station controller is also one of the elements from the base station subsystem, which control the radio network. Of course, it is a device used in a cellular network to manage and control one or more base transceiver station. It also acts like an interface between the mobile station and the mobile switching center MSC. Furthermore, BSC is performing several important tasks such as responsible for allocating frequencies and time slot for mobile device to communicate with BTS, keeping track of call and provide handover between cells. It also manages the BTS power levels, traffic local, and send control signal to BTS for optimizing the network. So as you can see in this picture, the BSC is in the scope of transmission network in the middle between BTS and TCSM. Okay, let's move to the last element. The last element is the transcoder and submultiplexer. So, transcoder and submultiplexer are used between the BSC and MSC. Physically, they also present in the MSC location. Most importantly, the TCSM is capable of two functionality. The first one is transcoding of speech signal. So, for the functionality, I will guide you to understand first about what is transcoder. So, transcoder is a device or a software application that convert one media format to another. For example, it can convert an audio file from one codec to another, or a digital audio stream from one compression format to another. So the second function of TCSM is submultiplexing of the PC signal. The same, I will guide you to understand about the definition of what is submultiplexer. Submultiplexer is a device that divides a multiplex signal into smaller substreams. This is useful in broadcasting or transmission scenario where multiple video, audio, or data streams are combined into a single multiplex signal for a transmission over a signal channel. For example, you can see in this picture. In the picture show about the submultiplexer. Of course, submultiplexers are located at the same place as the transcoder. In this picture, show us about the 4 PCM signal coming from the MSC are multiplexed to 1 PCM signal toward the BSC. This is the sample of the functionality of submultiplexer. But note, the figure may be different depending upon the equipment manufacturer. But the question is, what is PCM or what is pulse modulation? After we have been discovering with this question, we have found out that PCM is a digital representation of analog signal. It also a technique used in digital communication system to transmit analog signal over a digital transmission path by converting them into a series of digital binary pool pattern. The PCM is also used in various applications, including digital audio, video, and data communication. So, let's take a look to the second section of this chapter. After we have been discovering about the basic of transmission network planning, okay, let's jump back to the next section, which is transmission network planning process. The goal of transmission of network planning process is to generate a network plan for the transmission network that would provide high quality network with an immense amount of spare capacity of the very low cost. Additionally, as a transmission planning engineer, they have to use their expertise in balancing three factors. There are cost, quality, and capacity. Generally, the process of transmission network planning includes 5 main parts before the final plan is generated. As shown in below figure, you can see the first part is about the network requirement. The second is about pre-planning. Third is about the site survey, LOS, and site selection. 4 about the microwave link planning, and the last one is about the detailed planning. So let's take a look to the first part about the network requirement. So first of all, the process begins with data collection. This includes requirements for capacity and quality that lay the foundation for the whole process. Moreover, it also requires other essential information, including what transmission equipment is available, such as capacity, quality, target, tool for transmission planning, include link budget calculations, and topology that would be used. So, let's move to the second part. It is pre-planning. This part focuses on the dimensioning aspect of the transmission network. The process starts with the input from the radio planning engineer. It involve determining number of base stations needed in a region and connecting them. Then the transmission planners start defining the quality target for the network and decide where the transmission network should be heading. In fact, in order to get a better idea to decide the position, they will do think about the transmission product available such as radio, base station controller, information on the media, and an imaginary network topology. If defined or even the topology principle that would be used in the transmission network are formed. Thus, the final work designed after the whole process is quite different to the one at the stake, so all along the media of transmission is considered. Thus, if microwave transmission is to be used, then the link budget aspect have to consider as well, so that the link design meet the availability and quality target. So let's move to the next site survey, LOS, and site selection. After finishing the pre-planning part, the next part is site survey, LOS, and site selection. So, what is site survey? Site survey is the process of physically inspecting and evaluating potential location for communication equipment installation. Its objective is to ensure that the location is suitable for the installation of equipment, can provide inadequate coverage and signal strength, and also meet desired network performance requirements. So, what is LOS or line of sight? LOS is the clear path between communication points that enabling radio signal to travel unobstacled by any objective like building or trees. It is critical for wireless communication because the signal strength and quality decrease as obstacle block the signal path. Furthermore, a clear LOS in vitro for network planning as it affects the coverage area capacity and throughput of the wireless network. So let's move to the next question. What is site selection? We have found out that site selection is involved identifying and selecting the best location for placing communication equipment that support the network objectives. Anyway, factors that influence site selection include LOS, coverage requirement, infrastructure availability, power availability, environmental, and regulatory consideration and cost. Of course, site selection is crucial in network planning as it directly impacts network performance, coverage area, and deployment costs. By these three explanation, we can assume that the site selection is basically a radio planning issue, but the transmission planner engineers should get involved in the early parts so that it will be easier to find sites that have the data LOS with other sites. Most importantly, the LOS process should be done very professional because once a site is constructed and there is no LOS with another site, then there is a big loss for the network owner. The next part that the network planning engineer should follow is microwave link planning. So what is microwave link planning? The microwave link planning is a crucial step in the network planning process for establishing communication link between two or more points using microwave frequency. It is involved determining the optimum placement of microwave antennas and equipment at each end of the links, identifying any possible interface source or optical, and deciding on appropriate transmission frequencies, modulation schemas, and power level. Thus, when microwave is in the medium of transmission, the link budget calculation should be done such that the availability and quality are met. In this point, the calculation must be based on the ITU recommendation. So, what is ITU? ITU, or International Telecommunication Union, is a specialized agency of the United Nations that responsible for regulating and standardizing information and communication technology worldwide. Overall, microwave link planning plays a very important role in ensuring the smooth operation of wireless communication networking and minimizing the possibility of network outages or disruption. So let's move to the last part of the transmission network planning process. It is about detailed planning. So the detailed planning is a stage in the network planning process that involves in creating an optical plan based on the high-level plan developed in the previous stage. This stage involves detailed design, specification, and documentation of the network infrastructure, which include the network topology, technologies, protocols, security, and maintenance requirements. More than that, it also considers factors such as cost, timeline, and resource requirement. Furthermore, the output of detailed planning is a comprehensive plan that includes a detailed breakdown of tasks, timeline, and resource required to implement the network solution. So, after we have been crossing several stages from the network requirement to pre-planning, continue to site survey, LOS, and site selection, to the microwave link planning until the last one, digital planning. Finally, we reached our goal. That is the transmission network plan. But overall, the goal of transmission planning is to balance the network capacity, quality, and cost. However, the process looks very simple in theory, but in fact, in practice, it is much more complicated. Thus, in order to make student or to make all learner to be more easier to do this, our group will introduce the next section, which is for course and give more detail about the transmission pre-planning.
Good afternoon, teacher. My name is Lam Heng. I'll be continuing from my French part minute. So first of all, I'll be presenting on the topic of transmission pre-planning. The process of transmission pre-planning involves determining the number of base stations needed in a particular region and also connecting them together. During this process, we take into account about the information about the existing infrastructure, which also include their capacity and also the site location. In order to determine the required capacity of each link, the transmission planner must consider the traffic and the ability to make use of PCM, which is postcode modulation links. PCM is a digital representation of an analog signal that is used to carry traffic and signaling from the T or H, which is a transceiver, and also the operation and maintenance signaling, shortly known as Q and signaling, and may have bits for synchronization and loop control depending on the topology. So moving on to the next slide is about one PCM connection. So as you can see from the picture on the right hand side, one PCM connection has 32 time slots, with TS0 used for link management and TS1 to TS31 used for traffic and signaling. The bit rate for each time slot is 64 kilobits per second, and the TCH, which is a traffic signal, can either be 16, 32 or 64 kilobits per second, depending on the type of the signaling. So moving on to the next slide is about the postcode modulation requirement on the A-bits and the Ether interface. The transmission planner also needs to define blocking parameter for the A-bits and Ether interface. For the A-bits interface, it is usually around 1 to 2%, and for the Ether interface, it is usually around 0.1 to 0.5%. Spare capacity is also important for the future network requirement, and radio planning engineer determine the number of best transceiver stations and the TRX. The transmission planner then use this information to determine the number of traffic channels and capacity of the Ether interface. The number of TRX per base station is determined by the required number of time slots for each TRX and the required number of signaling time slot, which can either be 16, 32 or 64. So you might wonder what exactly is A-bits and Ether interface. So they both are interfaces used in cellular network, especially in GSM, which stands for Global System for Mobile Communication Network. A-bits is an interface between the base receiver station and the base station controller. It is a digital interface used to transfer voice and data traffic between the base receiver station and base station controller. The A-bits interface is responsible for managing the communication between the base station controller and the base receiver station as previously mentioned, including controlling handover, power control, and synchronization. Ether, on the other hand, is also an interface between the between the base station controller and the mobile switching center, shortly known as SC. It is a digital interface that carries voice and data traffic between the base station controller and mobile switching center. The Ether interface is responsible for managing the communication between the both, including call setup, call routing, and mobility management. So moving on to the next slide is about the equipment location. So during the nominal phase, this planning phase, we also need to determine the location of the base station and also the transmission and control subsystem module, shortly known as TCSM. TCSM should be placed near the mobile switching center to minimize the transmission cost. On the other hand, the base station controller should be removed from the mobile switching center in order to save on the transmission cost. Remote base station controller locations serve a large number of base transceiver stations far from the mobile switching center, while a co-located base station controller is preferred for metropolitan area with heavy traffic, which means for the place that are downtown or heavily populated, like highly developed cities. So moving on to the network topology. So selecting the proper network topology may lead to huge saving in the transmission network, and there are a lot of different kind of topology, but in this presentation we're gonna focus on 4 main types. They are point-to-point topology, star topology, chain topology, and loop topology. So moving on to the first one is about the point-to-point topology. So about the point-to-point topology is basically a direct connection between the base station and also the base station controller, as you can see from the picture. And this one is developed and heavily used during the early phase of network evolution. And the drawback of this kind of topology is that its capacity may or may not be fully utilized, and the protection of this kind of topology will add some more expense. So moving on to the second topology is about the star topology. So as you can see from the picture and also the name suggests, it shapes like a star. For this kind of topology, capacity can be better utilized with cross-connect equipment, and this one is relatively simple to implement. But the node failure may result in the loss of traffic coming through toward the base station controller. And just like the previous one, the protection is also expensive with this kind of topology. So moving on to the third topology we have here is the chain topology. Chain topology connects sites that extend from one region or city to another region or city. This kind of topology is used for connecting sites on a highway, and unlike the other two, the capacity of link is usually fully utilized. But the drawback is that the last link of the chain can be vulnerable without any proper kind of protections. And then there's come the last kind of topology, is the loop topology or the ring topology. So loop topology is an extension of the chain topology, where the last link of the chain is connected back to the base station controller. So this kind of topology provides protection without additional hardware redundancy, which means we don't need extra hardware in order to protect it over the chain topology. But this one requires additional node that can control loop and protections. So these are the four main topology that we have in our presentation. But in the real world application, a transmission network will consist all of above mentioned technologies, which means they may use different topology at once. Transmission planning engineers should balance between the technological advantage with the cost involved, keeping in mind the strategic importance of the site before designing which topology should be implemented. So moving on to the next topic is about the site selection and line of sight survey. The site selection process for radio and transmission planning engineer involves choosing sites with different characteristics. Radio planner prefer lower site to avoid interference, while transmission planner need very high site for connectivity to other sites. So there's a contradict between the preference of the radio planners and also the transmission planner. So there's come a compromise. So they both must agree on the importance of connectivity, and compromise may be made on the height of the site. In some cases, they have used one kind of solution, is the repeaters. Transmission planner use repeater for important sites that are low or between high buildings. Repeaters are high buildings with transmission equipment but no base station. So moving on to the next topic is about the radius of the Fresnel zone. The Fresnel zone is basically an imaginary ellipsoid between the transmitting and the receiving antenna, as you can see from the picture. It is where the distance covered by the reflected ray to the receiving antenna is half a wavelength longer than any direct ray from the transmitting to the receiving antenna. The size of the Fresnel zone depends on the frequency and the distance of transmission. For the clear transmission, the first Fresnel zone should be kept 100% clear of obstacle between antenna. And engineers should also allow for some clearance in order to avoid signal loss. And its size can be calculated using the formula below. As you can see, for the D1 and D2 is the distance from the antenna to any given point on the ellipsoid. And for the F is about the frequency, and for the D is about the linear distance between the antennas. So as you can see the formula here, this is how the size can be calculated. So moving on to the next slide, it's about the link budget calculation. So link budget calculations are done in order to determine the suitable path length for receiving the desired signal level, and these calculations are then used to determine the phase matching in order to counteract signal loss. So the first factor in calculating phase matching is free space loss, shortly known as FSL, which depending on the frequency and the distance covered. And the second factor is the gain of the antenna, which can be calculated using the equation 3.3 or 3.4 as you can see on the slide. So for the figure 3.3, you can see the formula where G is the gain of antenna in decibel, A is the area of the antenna aperture, E is the efficiency of the antenna, and lambda is the wavelength. And this formula can be further simplified and changing the parameter to the formula of the figure 3.4 as you can see below on the slide. So this is how we calculate the link budget calculation. Now moving on to the next slide is about the propagation phenomenon. So different factors such as weather and terrain beyond free space loss can affect the signal level received. Understanding the propagation phenomenon is crucial before working on the link design. The engineer must account for climate change that might affect the radio reflectivity and also the K factor. So about how to calculate K factor, here you can see the formula. K is equal to 157 divided by 157 plus dn over dx, where K represents K factor and represent the number of base stations in the network, x represent the average height of the base station in meter, and dn over dh, which is a derivative, is represent the changes in the number of base stations per unit change in height. And on the right hand side you can see the visualization of different number of K. So you can see here. So moving on to the next slide, it's about fading. Fading of the signal level can be broadly classified into two major kind is flat fading, and also another kind is frequency selective fading. Flat fading include two other minor kind is ducting and rank annunciation. Ducting is a phenomenon where the atmosphere traps signal under certain conditions, deviating from the original direction. On the other hand, rank annunciation is when rainfall causes annunciation in microwave signal with losses depend on various factors. So another kind of fading is selective fading. Frequency selective fading deflects on the signal but not completely. It is expressed as a probability of fade. And engineers should also consider other types of K fading such as K fading and diffraction fading. Atmospheric fading due to oxygen and vapor can also occur, and other factors related to natural phenomena such as snow and sun and dust should also be considered. So after understanding a topic about the fading, we should also understand the design principle for microwave link. So observing climatic conditions inform microwave link designs. Engineers need to follow certain principles when designing microwave links, including a sufficiently large phase margin needed for handling signal degradation. The first phase zone can be kept obstacle-free for K equal to 3.3, and clearance should be 0 for hoops over and under 15 km for K factor of 0.5 or 0.3 respectively. Overwater hoops should be avoided, but if overwater hoops are unavoidable, antenna height should not have the reflection point falling over water. Also, higher antenna height should be chosen in area with higher probability of cave-fading or ducting phenomenon. So these are the principles for designing the microwave link. Moving on to the next slide is about the error performance and availability. So after designing, engineer must test the link performance, and error and availability targets are used to measure performance. Error performance objectives are measured against standard values, and the standard value always vary. But the ITU, which stands for International Telecommunication Union, recommend a standard which is called ITU or T326. They recommend using this standard in order to test the error performance and also the objective. So after finishing about the transmission network planning in 3.3, now we moving on to the 3.4, which about the detailed transmission network planning. So moving on to the first point is about the frequency planning. So microwave links operate in area with many links and source of frequency. Efficient frequency planning prevents interface like infrasystem, interchannel, interhoop, and external interference. In the microwave network, the interchannel and interhoop interference are most important. Co-channel interference is caused by both signaling being 90 degree or cross-polarized, while adjacent channel interference can both co-polarize or cross-polar. Adjacent interference prevented by using a non-consecutive frequency bands in the same or adjacent links. So continuing about the frequency planning, inner hoop interference caused by unwanted signal at the receiving antenna, and interference can be prevented by using different frequency spots as source of interference. Techniques like using different polarization and tilting of antenna can be the remedy for the interference, which means it is how to stop the interference. And network reflection can cause interference addressed through antenna tilting, power reduction, or transmitting antennas. So moving on to the next slide is about the time slot allocation planning. So efficient utilization of PCM connections require understanding time slot allocation principle and methodology. So as you may recall from our slide about the one PCM link, one PCM have 32 time slots with TS0 for link management, and a 2 megabit per second signal is then converted to 16 kilobit per second channel by the transcoder or submultiplexer. 16 kilobit channels are further converting to 13 kilobit per second traffic, and 3 kilobit per second signaling on the air interface. Time slot allocation involves allocating traffic channels and time slot for traffic and signaling, with space for management bit, and time slot can be allocated linearly or in block fashion, with standard block assigned to respective or T or X. So the allocation scheme shown in figure 3.5, which is the same slide about the one PCM link, allocate the traffic channel time slot 1 to 24 with the signaling confinement lower part of 2 megabit per second signal, and the time slot 1 to 3 reserved for traffic and signaling for T or X1 and T or X2 only, and also the time slots 4 to 7 kept empty for future cell capacity expansion. So moving on about the 2 megabit per second planning. The routing of 2 megabit per second line is important for time slot allocation and detailed planning. Planning involves planning routes and determining the number of 2 megabit per second ports at the base station controller. In some cases, one PCM can be shared between multiple base stations, but the required number of ET ports at the base station controller remain 1. Changes in 2 megabit per second plan in upcoming network must be tracked by planning engineer, as they may affect the ET port allocation and the code modulation, signal utilization. So moving on about the synchronization planning. So synchronized planning is also important to prevent bit errors in the mixed network. Quantum mechanism dynamically accommodate phase variation, and proper synchronization planning eliminate this error. Good network synchronization requires a clock distribution with primary reference clock serving as the master clock, and slave clock should be locked to higher accuracy clock. Synchronization is needed for click-free flow movements throughout the network, which require accuracy of 10 to the power of -8 for GSM network. So moving on to another topic is about the transmission network management planning. Transmission network management planning is essential for component capability for a future expansion. The network management system, shortly known as NMS, provide NE, which stands for network element and configuration, alarm, fault, performance, and security management. The NMS function based on the master-slave protocol, which have been previously explained, and with the planning starting by selecting the master and the management bus parameter. The master capacity and speed in managing network elements vary. So about the last slide of our point 3.4 is about the transmission network management planning. Management bus speed range from 1200 bits per second to higher rates. Defining the management bus involves topology, protection scheme, and network element associated with a particular network element. Parameters such as addresses and identification speed must be defined for managing network elements depending on the management system type and also the capacity. And the engineer need to understand the type of the master used and how many channels are transferred and controlled. So that's all about my point. So let's move on to the next presenter presenting about the next topic. Thank you, teacher.
Let's move on to 3.5. My name is Limpanat. I'm in group 3. I'm going to cover on 3.5 the transmission network optimization. So before we move on to the transmission network optimization, I would like to cover what is the transmission network optimization. So the transmission optimization, it refers to the process of improve the performance, reliability, and make it more efficiency of a transmission network, which is a network that connect with a different part of the cellular network, such as like a base station controller, or we can call it a BSC, transcoder, and core network element. So when we're talking about the transmission network, we are involved into the planning, designing, and deploying when we try to introduce some network, and monitoring and the transmission network to meet the requirement of the capacity and quality, coverage, and the cost. So what is the benefit of the transmission network when we do it optimization? So the one benefit, we have 5 benefits. So the first one is improve the network performance, make it quality of a service, such as reduce latency, packet loss, and jitter and interface. 2 is increase network capacity and the coverage is make us can more wide range of the area, such as a higher data rate, more user, and wider service area. 3 is reduce network cost and operational expense, such as like lower power consumption, maintenance, and upgrade requirement when we need more network to improve its speed, enhance network reliability and uh, vulnerability, such as like higher uh, latency, resiliency, and full tolerancy. And the last is a better network, and it also provides us the scalability and flexibility and make it more easy to integrate a new technology, service and feature. So let's move on out of the sub point 3.5.1, the basic of a transmission network optimization. So in the past, when we're talking about optimization network, we talking and focus on the network of the ratio network optimization. So it also talking about the transmission planning that we talking of that we also talking about the line of sign job. And uh, one study have shown that the transmission network that is the core and also the most important role play in the transmission efficiency, make it more efficiency. So let's move on to the 3.5.2 transmission network optimization, the process that we're talking about, the process that we optimize the network. So let's move on to subpoint is 3.5.2.1, the process definition. So uh, the transmission network optimization is statics, and it also starts when the problem are defined and verified, and it also involves to the planning that we make on the data and the target. So for the planning, it also helps us to optimize the cost, the quality, and the requirement, the time frame. And it go into the master plan to prepare and implement after we planning and grab the period before the next optimization circle. It's not like or unlike ratio network optimization, transmission network optimization is not ongoing the process. And this is the figure that show the process that we optimization the network. So for the network capacity analysis that we refer to assessing the network reliability that based on the user demand, available bin rate, and the capacity of the various network. So for the demand, we refer to the amount of the traffic or data that is expected to transmit over the network within given a time frame. And another is network quality analysis that we focus on the quality of the service that provided by the network, and then it also involved to the planning, and it go to the master plan. So let's move on to another point is we talking about the capacity analysis. So what is the capacity analysis? The capacity analysis, it refers to the process that we evaluate of the current and the future traffic demand of the community network that we have, that we can ensure that network is capable of the handle in typical level of the traffic without experiment contrast or performance degradation. The analysis that we involve to the identify of the current capacity of network that we expect the increase in the domain that to determine whether this network configuration can accommodate the project growth or not. So before during the initial of the network or the mobile network, so the focus is on the connect base station to the base station controller timelinely manner, and it also neglect the topology design to under utilization connect media can occur. So when the mobile user increase, it can be led to the network. It also can crash, and we need to find the solution to increase the RTX and X size. So the RTX is like my friend in mentioned that there are the transceiver that enable the base station to send and receive the audio signal on different frequency, and the technology upgrade may be necessary to improve the performance, such as upgrade to 2.5G or 3G. So when we talking about the capacity optimization, the process we also have end up with a two float or situation. So how to use the excess capacity efficiency, and how to increase the capacity without minimal disruption to network functionality. So how, and also we also coming up with one more question. So how should the capacity analysis should be done? And it involves to the engineering. It depends on the engineering, and engineer should be collect all the data that relate for the region where the capacity analysis is to be performed. And the data also, what is the data help us? So the data is able to understand the current network situation and prediction the future network demand. And data, when we collect, we based on the information, engineering can plan how to optimize or increase the network capacity to meet the customer need and expectation. So another point is the transmission plan engineer should calculate the existing and forecast the capacity for each line into the network. In identifying the base station, use the laser of the optic cable and assess capacity utilization of the other side. So we also consider the replacing the laser line with the microwave radio to increase the capacity and create the topologies. There is by increase the protect level. It also give the example in the figure of table 3.2 that show the how it improve when we replace the laser line with the microwave radio. So this table is show the capacity that we replace the laser line with the ratio well. It increase. You can see the last after and before. So in case what if new site that getting add into the spot during after optimization the process, so then the capacity increase, the particular line region should be considered apart from the considering impact of the new site. and the result of capacity plan analysis should be very well to understand, and effects on capacity and cost should be analyzed before making recommendation for changing master plan for implement those recommendation when the new size is getting at into the hotspot. And we move on to another point is quality analysis. So what is the quality analysis? We might be analyze the quality of the network or the service. So so quality analysis is the process that we evaluate of the quality of the products or the service based on the set of the established criteria of the standard. So we based on the standard or the some criteria, and the quality analysis that we involve to the identify the measuring analysis and improve the variant aspect of the quality such as performance, reliability, functionality, usability, and consumer satisfaction. So uh, the quality degradation of the network we may due to many reasons. There is include the degradation of the microwave line performance due to the progression condition, some condition, or degradation in network quality is due to interface and synchronization that will relate to the some problem. And this 4 point is the more common that involved to the degradation of the network quality. So the first point is microwave line. They can be expensive, can be experience quality degradation due to the variant and prediction progression. The condition mean the condition that we can that predict it will gonna happen that make our quality network down. So the condition is such as padding, layering, ducting, and attention. Ducting to rain when it raining, the signal is faded, and it is necessary that to find the cause and solve it the problem when the signal is faded, and the quality line is must in term the error, the performance, and available analysis. So the quality target are checked and redefine the process of the data collection start. So the data that transmission planning engineer collect is generally that we include two is pre-planning and line performance. So the pre-planning and data and existing site inform such as topology, hop length, planning line, bucket calculation, frequency plan, or something else. And for the line performance data, collect data during and after line transmission and during the problem analysis. Collect data during a different time of the year or day. So we have to make some space to collect that data. Mobile phone statistic during that it's faded or non-faded press would be enabled better to understand the correlation between core drop and fading. And for the core drop, it will be from some problem. So for the core drop, it's have three. One is problem related to the interface and synchronization. That is also can the curve of the drop calling. Drop calling can result in the high traffic loss, which can be as high as few thousand minutes for a small like 100 site or under 100. Drop calling it can lead to a significant event loss for the network operator. So this is the figure that show the lost traffic a minute versus the percentage of the unavailable time per year from 10 sites to 100 sites in 1 year. So let's move on to 3.6. We're talking about GPRS, transmission network planning and optimization. So GPS is that we stand for of the 2.5G network. So for the transmission network planning is in the GSM network or 2G network remaining the same. It also the same, the GPRS technology implement. So PCU dimensioning is important aspect for the transmission planning engineer to consider for the GPRS network. So what is the CPR, the PRC is stand for the packet control unit. It's a component in the GPRS, or we call it general packet ratio service network, that handle the packet data traffic between the mobile device and the core network. So the PCR is allocated in the base station controller, and it's manage it's used to manage it's used to manage 2.5G network or packet traffic. It responds the manage of the GPRS. So the main aspect for the dimension of the PCU in its capacity, with expect to there have 5 points. One is minimum number of the PDP content, minimize number of RTX. Like I mentioned, RTX is the stand for of a transceiver, and minimum the number of PTS, minimum number of PCM line toward the RBIS and toward the gigabit interface, as well as the traffic on the gigabit interface, and minimum the number of the location of the area that routing the area. So for the optimization of the transmission network of the 2.5G network is quite similar to the 2G network. There are two important aspects related to the heavy loading GPRS network. So the first point is that is during the line phase there are maybe not change requirement in the existing 2G network, as there is less traffic. However, once the packet data users start increasing, the capacity might be need to review, and the existing configuration might be need to be upgraded or not. So the second aspect related to the coding schema used that we use in the 2.5G network, where where we are launching the new schema is change the bit time slot location. And let's we move on to the 3.7. It's H transmission network, or we call it E network. And H network transmission planning is process is similar to 2G or 2.5G network also. And for in this point we're talking about the dynamic abyss that we add functionality that we add into the H network to increase the data rate. So it's important the concept in H to we need to design the network. So for the PCU and the base station dimension, it also important in the H transmission network design. And a bit interface in H network is dynamic, while the GPS and PRG network is static, and the GP in the GSM or GPRS network for the TRH channel, it already mapped into the orbit PCM time slot. And for the capacity, it the situation dynamic and variant based on the number of the active for the user. So dimension of the orbit interface is more complex in the H network compared to the 2G or 2.5G network. So this is a picture of the orbit interface. It stays between the base station and base station controller. So the sub point is the 3.7.1 is we're talking about the dynamic orbit functionality in the H network or E network. Optional phrase keyword that we use in the H network, we use to change a data rate from 8.8 to 59.2 kilobyte. But for the data traffic, it requires more, 16 kilobyte with a bit channel. And for the dynamic a bit poor, it would be introduced that it can handle this, because it's dynamic. It's not like 2G or 2.5G network that is static. So for the DAP, it's consists of the group of the ABI channel with a minimum of the one time slot, and the minimum is depending on the system capacity within one PCM. And for the standard GPRS, it's used CS2 or CF3 and CF4. It can also use the EDPA resource when they allocate into the EGPRS Toriboris. So what is EDPA? So EDPA is refer to the group of the dynamic abyss that is allocated into by the base station controller for the H data cell, that when it needs a specific using a CS3 or higher. And the time slot in the abyss of the H network transmission is the most the same as that of bits in the GP, GSM or GPRS network. 2G or 2.5G network is similar to H also. So the traffic is on the traffic channel or the orbit, it occupies 16 kilobit sub time slot for the voice and the data rate is up to 16 kilobit or more than that. For the signaling channel request for TRX and base and BCF are the same as the of the G2 or 2.5G network, and the pilot bit of the synchronization it can be accommodated in the TS0 or TS31 of any other slot time. And for the another point is a dimension of the dynamic of the orbit. So the dimension of the orbit is the Q call in the H network planning. So orbit in the 2G or 2.5G allocate the whole capacity of the TRX in irrespective of this, while the DPA requests a dynamic slot time location of the packet data in the MCS greater than 2. So for the designer it should be referred to the system capacity and product information to determine the DPA pool size. So designer should refer to do that, and the number of the bit channel is increased with the added signaling, and it also and the subtime slot are requested for the from the pool, and the number of the slot time is located exclusively 1 to 4. It depend on the handling capacity, and the number of the time locate is located to the DAP. It cannot excess 30. And and the dimension of the dynamic orbit, we are involved to determine the number of the time slot that need for the pool user of the packet data transmit in the H network, E network. The goal is to ensure that the orbit interface is does not become to the bottlenecks for the air interface throughput, and the co-factor of the go-to that as is the number of the ratio time slot that request for PS traffic and blocking that could occur on the orbit interface that we are considered during that dimension. So this is a formula that we use to calculate of the PCM time slot. So DPA that we can determine. So for the n is that is represent to the number of the time slot that available in the pool. P is the channel utilization of the H channel in the air interface, and N is the number of the traffic channel used in the air interface. B is the blocking probability of the PID is a probability, so it might be not the ensure number at all. So let's move on to to another point is 3.7.5 is for the impacts of the dynamic orbits on the transmission for the network design. So in the H network, it have 9 time slot from the site. The configuration can be used in the DPA, and so we should it should be determined whether it's 9 are configs or not for the network. So with the MSG MCS G coding schema, it's like a 9 time slot. So only user can use the system at the minimum of the data rate of it might be 59.2 kilobit. So if more user request to use this schema, so the system will start sharing its resource, and the throughput on the air interface will be go down. So in case in this schema is allow only 9 user to use it. So and if there are more user to use this schema, so it will share and will reduce the speed of the network. So and it also advisable to be more time slot in the pool to maintain the throughput also. When increasing the number of the time slot, it will require more the PCMS, which will affect on the network cost. So we will spend more money on that. And the number of the time slot planning for the DPA, it should be balanced between the throughput and the cost also. Let's move on. Our last point is 3.7.5 H transmission network optimization. So the transmission of network optimization process is similar in both GSM and H network. So there are two factors is need to be considered in the H network. Is dynamic nature of the orbits and the variation of the air interface throughput due to the bottleneck that created by the orbits, and the pool of the time slot that return of the packet data, but the number of time slot is used for pool is static. So if the number of the package service user is increased in the network, so the optimization may be necessary to increase the time slot in the pool, and in the increasing the increasing number of the time slot in the pool is maybe increase the number of the PCM. It will request more in the base station if you can affect on the cost. And that should be it for our team presentation, and thank you for your paying attention.